我第一次听到这个、看到这些东西呢，是从YouTube 上面看到他的演讲。后来我也觉得这个就像邱先生刚才说的那样，我觉得这本书非常 fascinating， 而且对我们两个来说，翻译这本书从中文的意义远远不止是在把这些东西介绍给这本书介绍给中国读者。我第一次听到作者的名字是1981年，就像作者所说的，我弟弟写信回来说，他除了修课以外，还在准备博士资格考试。他遇到了跟康穆拉、瓦法在一起讨论问题。对我印象最深的是，他想了1个星期没想出来的问题，康穆拉花了20分钟就解决了。所以他跟他们交流是得意非浅。当然，他们的交流不完全是在物理上。很不幸，他在92年得了脑炎，后来就不再能从事物理方面的研究。康穆拉在这30多年之内，他们的友谊继续在发展，而且在无微不至的，在各方面无条件的帮助他提高他，而且动员了很多人来帮助他的身心健康，包括邱先生也提供过一个机会，让他修改一本书。所以翻译这本书对我们两个来说的意义是非常重大，远远超过了这个本身翻译的意义，是对他们30多年的友谊致以最大的敬意。So I just wish all the Chinese version could we keep the original English versions vividly. Discrimination could be more entertainment and enjoyable of reading. And anything lost in the translation, you could get that from today's talk. Thank you.
Thank you. Thank you. Thank you, Litian. Thank you so much. So let's begin the talk with these kind remarks by Litian. So if I can have the, yes, there it is. Puzzles to Unravel the Universe is the name of this book. And I'm happy to present it here. Let me just use my... So math and physics have had a long, beautiful history of interaction over many thousands of years. And different civilizations have contributed to it. For example, the Greek mathematicians and philosophers tried to use mathematical symmetries to try to describe physics. Other scientists all over the world, China, India, Islamic countries, all contributed one way or the other. Science is a borderless adventure. For example, Biruni accurately measured the radius of the Earth many, many centuries ago. Another example, actually, is, before I show this, how many of you think that the atmosphere of the Earth, the height of the atmosphere, was measured in last century? How many of you think it was measured last century? Raise your hand. How many of you think it was measured 500 years ago? Raise your hand if you think so. How many of you think it was measured 1,000 years ago? Raise your hand. Okay, so actually, yes, indeed, the atmosphere's height was measured about 1,000 years ago, not by sending rockets into the space, but by simple geometry. And the idea was, if you lived here, you will see the sunset when the sun is here, but when the sun goes down, even though you don't see the sun directly, the sky is still not very dark. It takes a few hours or an hour or more for the sky to get dark. The idea is that the reason the sky is not dark is that the sun still gets to some part of the upper part of the atmosphere, and you can see that. So when the sun gets down here, then you cannot even see the upper atmosphere, it doesn't get the sun ray, and then it's really dark. So using how long it takes for the sky to get totally dark, you can estimate the height of the atmosphere giving the radius of the Earth, which had been measured beforehand. So this way, you can see a simple application of geometry to a question about the height of the atmosphere. Quite remarkable. My area of research is string theory, and the aim of the string theory is to unify fundamental forces and particles into one framework. It tries to describe the smallest and the largest things into one mathematical object, strings. So the idea is that when we talk about particles like quarks inside the nucleus, in secret they're actually extended objects like strings, but they're so tiny it is hard to see that they look like a string. Strings interact with each other by two strings coming and joining and forming another string, or going backwards, one string going and splitting to two strings. It's a very geometric theory interactions, which describes all the interactions in nature, including gravity, interactions of electrons with each other, as well as strong forces and weak forces. This area is very mathematical, and it involves many abstract ideas. Dimension of a space is more than 3 dimensions of space at one time. In fact, in string theory, is 9 spatial dimensions at one time. The shape and size of the other tiny 6 dimensions affect what we see in our universe. We assume that they are tiny, and that's why we don't see them, these extra dimensions, in everyday life. To see them, we have to have a much stronger microscopes in order to see much smaller dimensions. Now, the strings can wrap around these tiny dimensions, and these lead to insights about how the black holes work in our space and how the beginning of the universe may look like. So what is the space that tiny spaces are? We don't exactly know. Here I'm drawing spheres to depict them. Many popular examples include the Calabi-Yau manifolds that mathematicians taught us about, including Yau, and they have been extremely important for our understanding of the physical world. Now, you might think that it's very difficult to understand physical principles without knowing a huge amount of background. However, the highly mathematical aspects of string theory is typical of many attempts to connect physics with reality. Math is always in the center of a lot of attempts to connect physical thoughts with reality. But the question is, can we illustrate the connection between physics and math in a simpler way? This idea was the motivation for the course that I started when my wife Afarin recommended that I take this seriously, to start a course about trying to use puzzles, simple mathematical puzzles, to explain physical laws. Mathematical puzzles do not need much background. Nevertheless, they teach us something about the fundamental laws if we look at them carefully and clearly. So here, this kind of ideas led to this course that I teach at Harvard, and it led to the book that I wrote, Puzzles to Unravel the Universe. So this class that I taught had 12 to 15 students, and it is my favorite course to teach at Harvard. I'm going to teach it again in a couple months. So here, I'm going to give you examples of these puzzles that I share in this class with my students. But the difference is that I want to ask you to solve the puzzles. So you're going to help solve the puzzles. You're going to answer yes or no, and in this way, we'll try to solve the puzzles. So are you ready? Good. This is the English version of that same book. Okay, I'm going to have various topics. The first topic is symmetry and conservation law. Symmetry is very important in physics. Now, symmetry might sound boring, like if you have a triangle which has equal sides, you say, okay, there's a symmetry in this triangle of reflection, let's say. But symmetry principle turns out to be very powerful, especially when you combine it with conservation. Conservation, that things don't disappear. Conservation laws, things stay put. The total mass doesn't change, for example. So here I want to illustrate one example of a symmetry, and try to get your help in solving it. So here we have two containers, one green container, one white. We take a glass, we fill it with some of this green container, green paint, pour it into the white paint, and then we stir it nicely. And then we take the same amount, but now from this mixture, and pour it back into the green one. And then we mix it. And then we put it down. Yes, please go down. The glass is stuck there? No, it goes down. Good. So the question that I want to ask you is, which of these two containers has more mixture of the other one? In other words, does the green one has more white in it, or the white one has more green in it? Is the question clear? Okay. So those of you who think the white one has more green in it, raise your hand. Okay. Those who think the green has more of the white, raise your hand. Nobody almost, very few. And those who think they are equal, raise your hand. Okay. So, very good. So here, many of you thought that the white one has more green in it, and that is the intuitive answer, even though it's not the correct answer. Let me explain why it's the intuitive answer. It is the intuitive answer because when you poured from the green to the white, you took pure green, but when you took it back, it was mixed. So you're bringing some of the white back to the green. So therefore, the green is more in the white than the other way. That's the logic. But that's wrong, actually, it turns out, even though it's intuitive. Here, I want to use symmetry to show you that this was a mistake. What is the symmetry here? Well, to begin with, they had equal volume. There's a symmetry between the left and the right. At the end, they still have the same volume. Okay? Clearly, because we took the same amount back and forth. The total amount of green is equal to the total amount of white. So whatever in this mixture is not green must be white. And whatever in the white must be, which is not white, must be green. But since the total volumes were equal, if you switch them, they must be back to the original one. So they must be equal amount of mixture. So the answer is they are equal. And so if you think about it this way, you can kind of unmix it and kind of imagine unmixing them, and then you will switch them, put them back in the right place. So this kind of shows us that the conservation, that the mass does not disappear, and the symmetry between them kind of explains and deconfuses us. So sometimes symmetries are powerful, even though in this simple example that you see how it works. Now, symmetries are fun, but it turns out in physics, breaking them is even more fun. Now, breaking symmetries can be done artificially. I'm not talking about that. I'm talking about the notion of spontaneous symmetry breaking, breaking by itself. Now, you might ask, what does breaking a symmetry by itself mean? Our next puzzle illustrates that. So again, I want your help. We have 4 cities at the corners of a square. The cities are A, B, C, D. We want to build a highway system connecting these 4 cities in such a way that it is the shortest length of the total highway system because it costs money, and we want to minimize the cost. Okay, the question is which highways, and moreover, we want to be able to go from every city to every other city. Not necessarily directly, but through some path. Is the question clear? How many of you think the shortest highway system connecting every city is this? Raise your hand. How many of you think it is this? Raise your hand. How many of you think it is this? Raise your hand. How many of you think it is this? Well, this is the same, more or less. I shifted it down, so this is cheating. How many of you think it is this? Raise your hand. This turns out to be the answer. This looks crazy. This looks crazy because why does it look crazy? It looks crazy because it does not have the symmetries of the square. It has some of the symmetries, like the reflection A and B to C and D, but the reflection between AC to BD is lost. Namely, the reflection around the diagonal AD is lost. So if you reflect around that diagonal, you get a different system. What that means is that if you lived in city A, you can get to city C much faster than from A to B. So you have broken the symmetry. Not artificially, but by minimizing something. In physics, this happens, and what we minimize is the energy. So when you minimize the energy, even if you start with a situation that you had a symmetry, the minimum solution might break that symmetry. This turns out to be extremely important in physics. In fact, there's an example of this appreciated by the Greek philosophers already a few thousand years ago. And this is the way they reason. They had already, these Greek philosophers were very smart, super smart. They had already figured out that the earth is round. Now, they had noticed that the earth doesn't move. Like, it doesn't seem to move. So they wanted to understand why it doesn't move. Now, why would they think it should have moved is that they looked at the sky, the sun was moving, the moon was moving, everything was moving, but the earth wasn't moving. They wanted to explain why is the earth not moving. So they said, well, the reason it's not moving, this was their reasoning, is that the earth is at the center of the universe, and if it were to move, it would have to pick a direction. And picking a direction breaks the symmetry. So if it goes, for example, that way, you have broken the symmetry. And therefore, since the earth does not want to, since the symmetry is there, and symmetry breaking is a bad thing to do, that's why earth does not like to move. That was their reasoning. In other words, they say it's forbidden. You cannot move because it breaks symmetry. So their idea is very much ahead of their time. We use these kind of thinking even today about trying to explain physical phenomena using symmetries. But even then, Aristotle found a flaw in this reasoning. He said this is not a good reasoning. And to convince people that this is not a good reasoning was the following. He said, suppose you're at the center of a circle and you put food around the person, around the circle. So you're at the center of a circle and the loaves of bread is around the circle. Okay? Is that clear? The question you ask is this person going to move? Is he going to move? Of course he's going to move. Otherwise he's going to die of hunger. But it breaks the symmetry. He has to choose a direction. He does not care. He breaks the symmetry. Breaking the symmetry is a matter of life and death. He will break the symmetry to get the food. Is that clear? That's what happens. Even though the problem was symmetric, the solution breaks the symmetry. This is the origin of how Higgs particle, this famous particle which gives mass to everybody, including all of us, gets its mass. It's through such a mechanism, spontaneous symmetry breaking. So it's a very deep but simple physical idea. In fact, your bodies break symmetry. You might say, what? My body breaks symmetry? Yes, your bodies. Each time you go in front of the mirror, you should pay attention. You break the symmetry. How is that? Well, we live on the Earth, which has more or less, on the average, 360-degree rotation, horizontal rotation symmetry, right? So, and we have evolved on the Earth. Therefore, we should be rotationally symmetric, 360-degree symmetric. But, for example, our eyes are in the front. It is not like this. So each time you go in front of the mirror, you should remember that your body breaks the symmetry. Now you might ask, why does it break the symmetry? Well, I think it might be because, we had to go after the food. You see, we have to know where the food is. And we have to go after it. We don't need to go over all the circle. We need to go in one direction. In other words, the movement breaks the symmetry. What's the evidence I have for this? Well, on the average, trees are more symmetric. Right? Trees don't have to move. So it's consistent with that picture, that they are more symmetrical in terms of rotation than us. So your body spontaneously breaks the symmetry. And that's related to how you get your mass. So that's a kind of a cool connection. So as I said, it explains the origin of the mass, the Higgs particle, why there is more matter than antimatter, how the magnets work, and how the superconductor works. All of these are related to spontaneous symmetry breaking. So breaking the symmetry automatically has a lot of interesting physical consequences. Now, mathematics is really powerful. Now, you might think that you have to go very complicated math to have a really cool applications. Here I want to illustrate that even simple elementary school math could be interesting. We don't need to get too fancy. Math is interesting and it deconfuses us. So let me give you an example. Consider the Earth and the equator, and consider a belt around it, like this is a belt around the equator, and suppose you open it up. So you open the equator belt and it becomes this length down here. And then you add 1 meter at the very end. So it's a huge belt. You add 1 meter to the end. And then you wrap it around the Earth again. But now it's not going to be tight. It's going to be a little bit above, right? The question is, how big is this? How much does it come? What is this X? How many of you think it is like 1/2 meter or more? Raise your hand. How many of you think it's 1 centimeter or more? Raise your hand. How many of you think it's less than 1 millimeter? Raise your hand. Okay. Okay, I guess we have more or less covered the possibilities except between millimeter and centimeter. The answer turns out to be 16 centimeters, which is surprisingly large. But it's actually a simple math, elementary school math. Namely, the radius was 2 pi r if the radius of the Earth is r, and you added 1 meter to it. And that should be 2 pi times the new radius, which is r plus x. And so you find that 1 is 2 pi x, and x is 1 over 2 pi, which is 16 centimeters. Surprisingly large. However, the shock is yet to come. This is not the shocking part. Suppose we take this here, this part of the belt, and pull it further to the left, so that that side is tight, but this can go more. Right? We can push it further out. The question is, if you do that, how much further does it go? How many of you think it's going to go up to 1 meter? Raise your hand. Or 1/2 meter, let's start. 1/2 meter. Okay. How many of you think it can go up to 2 meters? Raise your hand. No. 120 meters, raise your hand. Absolutely not. Well, yeah, it is 121 meters. How do you know this? Well, this needs a little bit more than the elementary math I showed you. It just needs calculus. Just expanding sines and cosines in power series, you can immediately get this formula. I encourage you to check this formula. It's 121 meters. Unintuitive. So simple looking things can actually be very surprising. So our intuition is not necessarily good. Somehow our brain is not wired correctly to get these correctly. But math is a way to clean up our thinking. So it's very important. Another thing is that you don't have to get to deep, complicated math. And one particular example is continuity. One of the basic facts and important things I would say about topology is the notion of continuity. Basically, in physical terms, means things don't jump. They gradually to the other. The physical laws and all that share this property. We don't have this jumping situation. We always have something smoothly goes from one to the other, or at least continuously changing from one to the other. So continuity is an important principle in physics. I want to give illustrations of this principle. Again, we go back to the Earth. Again, consider the equator. Here we are trying to describe the weather on the equator. So we want to measure the temperature on the equator. So you open up the TV, they're going to say, today we measured the temperature on the equator. Okay, it's a boring thing, but somebody might do it. And of course, the temperature varies across the equator. It's not necessarily a constant. And then you ask the question, could it be that magically there are at least 2 points opposite relative to the Earth which have the same temperature, exactly the same temperature? Well, it could. Why not? The question is, does it function like this? In other words, suppose we only assume that the temperature varies continuously as you go around the equator. Does it have to be the case that there are 2 points opposite to each other on the equator with the same temperature? How many of you think the answer to that is yes, there will always be such points? Raise your hands. How many think it doesn't have to? You can arrange the temperature so it doesn't have to be equal at opposite points, at some pair of opposite points. Okay, the answer is that there always is 2 points opposite to each other which have the same temperature. And how do you see that? Well, suppose they are not equal. Consider a function which is the difference of temperature across from each other. There's a function f, okay? This function is defined on every point on the circle. Namely, you take the temperature on one point minus the temperature on the opposite point. Is that clear? If this function is ever 0, that means the temperatures on opposite points are equal. Is that clear? So all we have to show is that this function vanishes somewhere. But that's the way to think about this, that suppose you start with this and it's not 0 here. If you go to the opposite point, it flips the sign, because if you flip the order of these two, you get the opposite sign. In other words, if you go to the opposite corner, f flips its sign. So in other words, wherever you start, if you start with negative, on the opposite point you get to the positive, and by continuity it has to cross 0. So continuity shows there is a 0, and therefore there are equal temperatures. So this is a simple application of topology to physics. Namely, we're interested in temperature. The physical law tells us temperature varies continuously, and the simple mathematics tells you that temperature has to be equal at some point to the opposite. It does not need any deeper physics than continuity. So continuity is a basic principle of mathematics and physics, and it's very powerful. Another example is, if you measure the temperature and pressure on the Earth, there turns out to be at least 2 points opposite to each other on the Earth, relative to the center of the Earth, which have the same temperature and the same pressure at any moment. It's quite remarkable. It just follows from the topology of a sphere and the continuity of these two. Now, I will give you another example of the power of continuity. This is really cool, but unfortunately, the mathematics of it is a little bit more complicated. It has to do with gravitational lens, one of the features of general theory of relativity. So if there's a galaxy here, and if we are here on the Earth, and we are watching the galaxy, the light might come from different paths and get to you here. And the way this would work is that the light is getting bent by gravitational force. Einstein told us that the gravity can act on the light, and the light, by geometrical curving of the space, it could cause the light to bend. So if you're here on the Earth, you will see two images of this galaxy. So you can get multiple images. For example, in this picture, this region has repeated objects. For example, these four objects are the same quasar. And these three galaxies are the same, the orange ones. So it's quite remarkable. You're looking at the sky and you think you're looking at different objects, but some of them might be the same. It's just the light comes out different ways. You might be puzzled here that there are odd number of images here, 3, 5. Is that always the case? Do you always get an odd number of images? This is a fact. It turns out the number of gravitational images, if no image is blocked, of course you can block an image with your hand or something. If you don't image, if the light doesn't get trapped in a black hole, or if you're not blocking it, then it turns out you always get an odd number of images. And precisely less than half of them are inverted. So the 5 I showed you, 2 of them are inverted images. They're not like this, they're flipped. And 3 of them are straight. So always, less than half of the images are inverted. Now, how do you do this? How do you show this? Well, you solve the Einstein's equations. Well, that's too complicated to solve and show. It turns out you can prove this using simple ideas from mathematics. The topology and continuity shows this. How does that work? Well, there's this notion of a degree of a map. Degree of a map is basically, if you have a map from one space to another, you look at the pre-images of one point, and you ask how many points go to that, how many points get mapped to it. And then you count the number of pre-images with a plus or minus sign, depending on whether the orientation of the map is flipped or not. It turns out that the degree of the map does not change under deformations of the function continuously. So the degree of the map is what mathematicians call is an invariance of that map. You can count it, and it's going to be there as a number, which is always that, as long as your map is continuously deformed. So here, if you look at the situation, for the moment, suppose you turn off all the galaxies. Turn off all the matter. So there's a galaxy here, and you're over here. The lights go straight out if there's no gravity between us. So if you take a sphere near the galaxy, there is a map from the sphere near the galaxy to a sphere which passes through the Earth far away by just following the light ray. The light sphere at some point and hits the big sphere at some other point. So that's a map from the small sphere to the big sphere. If there is no matter between us, the degree of that map is 1, because it's an identity map. It maps every point on the sphere to the corresponding point. So the degree is 1. However, if you now gradually turn on matter, this function changes continuously. But the degree of the map cannot change because it's a topological invariant. So the degree of the map is always 1. So the number of images can change, but not the net number. The net number should always be +1. So if you get 3 images, then you must have 2 +1s and 1 -1. In other words, one of them should be inverted and 2 of them should be straight. So here you can illustrate it. This is trying to illustrate how that happens. So here you see this Earth. The geometry of the region is effectively, what I'm saying is that you can think about the geometry of the region of the imaging is flipped or curved like this. So here you only have one line passing. Oops. So here you see, for example, one image. And if you continue this, over the next one, over here you see there are 3 of them. One of them is inverted in the directions as you go around. And over here you get 5, and so on. So you always get these odd numbers. And that's related to the degree of a map. Now, but sometimes you need to get abstract. And sometimes you need to think abstractly. And mathematical abstraction is one of the powerful things we deal with in physics all the time. So here, I'm going to give you a puzzle. The puzzle is about ants. 4 ants on a plane. They are marching. The ants are marching at a constant velocity in different directions. So in other words, their speed is constant, but their directions are not the same, and each one might have a different speed than the other ants. What we know is that the ants collide with each other. All of them, we know they go through the same point at the same time, except for ant number 1 and ant number 2. We do not know if they go through the same point at the same time. In other words, we have a situation like this. The ants are moving. There are 4 of them, and 1 and 3 cross. And the question is, this ant number 1 and 2, as they come here, are they going to cross? Will they collide? How many of you think, yes, they have to collide? Raise your hand. How many of you think it does not have to collide? Raise your hand. Okay. It turns out the answer is they have to collide. But how do you show this? It turns out you have to use abstract mathematical thinking. What's this problem? Abstract mathematical thinking? Yes. You have to introduce an extra dimension, like in string theory. But actually, more specifically, like what Einstein did. Time is also a dimension. So this problem is not two-dimensional. This problem is three-dimensional. 2 space and 1 time. Why does that help us? Well, the ants are going at a constant speed. So if you project them into looking at it and where they are in space and time, they look like straight lines. So the ants are going on straight lines in space-time. Is that clear? So you have 4 ants. Each ant is going to correspond to a straight line in 3 dimensions. Is that clear? Moreover, we know that out of these 4 lines, all pairs cross. Why is that? Well, because they pass through the same point at the same time. That means the corresponding lines in 3 dimensions cross. Then 3-dimensional Euclidean geometry can be used to prove the other 2 have to cross. And how does that work? Well, let's see. You basically introduce time, and now they are marching in space and time. So you see the planes. The ant 1, 3, and 4 form one plane. The ants 1, 2, and 4 form another plane, but that plane includes the lines 2 and 4. Therefore, the lines 1 and 2 should be on the same plane because they're both on the plane 2, 4. So Euclidean geometry shows that 1 and 2 are in the same plane, And since they were going in different directions, they have to cross. It's just that. So abstraction allows you to solve it without doing any other work. Duality. One of the fascinating things in string theory is dualities. Duality means things that look one way might look completely opposite, and they would be equivalent. For example, like this drawing by Escher. If I ask you, what is this the drawing of? You could say this is a drawing of a day, in a white sky with the black birds flying to the left. If you looked at the other side, you say, no, 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 this is the story of white birds flying at night. If you look down here, you say, no, no, there's no birds here. They're just the fields, farm fields, black and white farm fields. Of course, they are all correct. Depends on where you're looking at. What we call is that we say there's a duality transformation taking you from one perspective to another. This is exactly, in spirit, what we do these days in string theory. Okay, how do we have a puzzle about this? Are you ready for this puzzle? How many of you like ants? Good, thank you. This is going to be the next puzzle. It's again about ants. We have a wire, actually not a wire, a ruler, 1 meter long, and we have a bunch of ants on this 1 meter long ruler, and they move with the speed of 1 centimeter per second. Now, they go at a constant speed, and when two ants meet, if they collide, they reverse the direction and they go the other way until they meet the other ant and they collide and they go back and forth. Is that clear? But if they get to the end of the ruler, they fall down. I'm sorry, but the ruler is only 1 meter long, so if they continue marching, at the end they just fall down. Okay? It's like this. So you have these ants, the blue one hits the orange one and then goes back, and then purple one and so forth, and when they get to the end, they fall down. At the end, all of the ants will fall down, unfortunately. But there's a puzzle for you. Where do you put the ants at the beginning, and which direction should the ants initially move, to the left or to the right, so as to maximize the time that the last ant is on the meter stick? Is the question clear? How many of you think a good strategy is to try to put all the ants towards the center and instruct them to go opposite, left and right, relative to each other? Raise your hand. How many of you think it doesn't matter where you put any of the ants? Raise your hand. How many of you think it doesn't matter where you put any of the ants except for one? Raise your hand. Okay. Well, it turns out that indeed the answer is it does not matter where you put any of the ants except for one. Why is that? Well, the reason is that we should not be looking at colorful ants. We should look at the ants in their natural color. What is the natural color of an ant? Black, thank you. So here I'm confusing you. I should draw black ants. So if I draw black ants, what happens if two of them collide? Well, they go the other way. But really, can you see the difference between the ants colliding, going back, and not colliding? Like, are they going through each other, or are they colliding and going back? There is no difference. That's a duality transformation. In other words, when the ants are colliding, instead of reversing direction, we can do a dual transformation to flip the identity of the ants and continue marching. Therefore, if you want to have the ants last the longest, you put one ant at the very end and say, go to the right, and that's the maximum you're going to get. It's not going to be that ant that survives. Some ant will survive the longest, namely 100 seconds. So I'm coming to the end of my talk, but this is going to be my last puzzle, which in fact is my favorite puzzle, because it teaches us about the methodology of science and scientists. This one, we are going to be all scientists now for this puzzle, and we are going to do experiments together. In science, we take examples, which means experiments. We do experiments. We then formulate a general principle based on these examples, the laws of physics. We predict what the laws of physics are. And then we come up with explanations why these laws work the way we think they do. And then, of course, we again go back to first one and step one and still do the examples, meaning we never stop doing experimentation, just to make sure we didn't make a mistake. This is the scientific methodology. Is that clear? So let's do a scientific experiment together. The experiment we want to do today might sound a little boring, sorry. The experiment is we take a circle and we consider points on the circle. If you take 2 points on the circle and you connect them, how many regions do we get in the circle? 2, thank you. So 1, 2. Good? So if you have 2 points on the circle, when you connect them, you get 2 regions. Suppose you take 3 points and you connect those. How many regions do we get now? 4, thank you. So 1, 2, 3, 4. In other words, 2 points, 2 regions, 3 points, 4 regions. Look for patterns. That's what science is, looking for patterns. We are doing experiments. The next experiment. We add 1 more point, 4 points. How many regions are we going to get now? Excellent, 8. 4 points, 8 regions. Do you get the pattern? How many of you think for 5 points we are going to get 16? Raise your hand. How many of you think we're going to get 15? Raise your hand. How many think we're going to get 17? Raise your hand. Okay, let's check it. The 5th point, we did experiment. We count 16. 2 points, 2 regions, 3 points, 4 regions, 4 points, 8 regions, 5 points, 16 regions. Why are we getting this? It's doubling each time. Why do we get doubling? The reason we are getting doubling might be that each time you draw a line, the region is either to the left or right, so there's a factor of 2 each time. That's it. So how many think if I have 6 points, I'm going to get 32 points, 32 regions? Raise your hand. Some people doubt that. You guys are super smart. Because if I do the next one, we end up getting 31. So it does not work. It does not work. It fails. We had the theory. I explained to you the theory. It is a wrong theory. The theory was incorrect. Experiments showed us it's an incorrect theory. We have to go back to the drawing board and find the correct theory. The theory was wrong. Okay? This happens again and again in science. We think we understood it. We do more experiments. It doesn't work, and we go back and find a better theory. It turns out for this one, the theory has actually been solved, and there's an answer, which is the number of regions goes like 1 plus n choose 2 plus n choose 4. And if this continued, if it didn't stop at n choose 4, you get a power factor of 2 each time. But since it stops, it gives you a different answer. So I've run out of time, so let me just say I hope I've conveyed the power of simple mathematical ideas in the context of physics. And there are many more examples like this in the book. Even the most advanced ideas in physics have simple mathematical underpinning, just like the puzzles we have discussed. Thanks for listening to my talk.
Yeah, thank you very much, Professor Waffa. That was a lot of fun. Questions from the audience now. We can take a couple of questions about the book or the presentation. Yes?
Thank you. What are the limitations of existing theories and why it is necessary to propose a superstring theory? Thank you.
The exact limitations of the theories is that, in the context of string theory, is that we do not know what is the fundamental formulation, what is the basic laws of it. But more laws of physics today are exactly correct. In fact, I believe that this is going to be always the case, that we are always going to find the analog of improvements of the laws. We are never at the end of the road. So all the laws are in some form approximate, and we have to figure out how to improve them. String theory is no exception. Of course, string theory is the most advanced understanding we have of fundamental physics, and in particular of how quantum theory and gravity can be put together.
More questions?
Over there, there's a question.
There is, yeah, maybe you can put,
You can.
yeah, there, next.
Good afternoon, sir. I'd like to ask a question. A photon is a boson and an electron is a fermion. What is it? Why is it possible to relate a photon, which is a boson, during an electron energy level transition? Is it energy that translates to a photon?
So just to make sure, when we say electron jumps, the electron doesn't disappear. The electron goes from a higher energy to a lower energy, and it emits a photon. So a fermion can go to a fermion and a boson. In other words, the total fermion number, mod 2, is conserved. So you start with one fermion, you ended up with one fermion and one boson. So this has to do with the property of the spin of the particles. Fermions have half-integer spins, and so half-integer numbers added up together, mod 2 is conserved, and that's the conservation of the number of fermions, mod 2.
Okay, thank you.
You're welcome.
Other questions? Yes?
Thank you. Sir, may you explain the laws of symmetry with group theory and the Noether's theorems? What does that have to do with our, the conservation of energy and the conservation of mass?
Yes, so symmetries and conservation laws are related, surprisingly, I would say. So the fact that if you consider physics at one place and move and do an experiment physics over here, turns out to be related to conservation of momentum. The fact that if you do the experiment today and repeat the same experiment tomorrow, the fact that the result doesn't change implies the conservation of energy. The way this works is through Noether's theorem, which tells you when you formulate physics in terms of minimal action principle, least action principle, that formulation leads you to connect symmetries to conservation laws.
Okay, thank you.
Yes?
Hi, nice to meet you here, Mr. Waffa. I'm a student from Tsinghua University High School, and my question is, what is the current research at the forefront of mathematics, and how do these studies help the development of human beings?
Well, mathematics is a huge subject, and of course, I'm not a mathematician, so probably you should ask Professor Yao this question, but I think math is a huge number of areas, and it applies to all sciences. So not just physics. And so it's a general framework to address things which you can quantify or have a framework for theoretic ones. Math typically is its answer. So which one is the forefront of it depends on which question you're asking. I would say that's probably the most exciting thing about math is that all math is useful for something.
I mean, how does the highly abstract mathematics drive concrete production?
Well, I try to give examples. For example, you remember the example of the ants? Or the example of the number of gravitational images? Those are abstract mathematical statements. But they have concrete meaning. The photographer of the galaxy sees 3 images. Say, why 3? Why not 2? Why not 4? Why are they inverted? So they will understand what they are seeing. So mathematics helps you put into place what our understanding is. A good way to summarize our learning and formulate our expectations about reality.
Okay, thank you. Thank you very much.
Over here.
Okay.
Here, there is a question there.
Yeah, okay.
Thank you for this funny talk. And I'm a math student, and I want to learn something about physics. And so I wonder if math students want to know something about physics and our universe. Can you give some advice or how to study or some?
Well, studying, there are standard textbooks in physics.
Oh, I know that. So
you're asking about which textbooks, or what is the?
What's the? Yes, because if you are like you don't learn math, I think when you study physics, you may have to like read more books. But if you study math, I think
yes,
it will help you. Like
absolutely, you have to study them both.
Okay.
I think the thing that I cannot overemphasize is that one without the other for explaining reality doesn't work. Physics you have to learn, math you have to learn, and trying to mix them is a great idea. So I think we have learned from history of science and history of physics in particular that math is an effective tool in solving or formulating physical laws. Of course, physical laws and their formulation have developed math too, like Newton's development of calculus is still going on like that in string theory, where we are developing new mathematics.
So their connections is like strengthening, like there are more and more connections between.
Yes, the connections are building up. New branches of mathematics are being developed in the context of physics because we have questions that we need mathematical help. So we have mathematical frameworks to build and address those questions, and vice versa. The ideas that come from physics suggest new mathematical structures that people had not studied.
Okay, maybe one last question.
Hello, Professor Vafa. I want to ask a question. Since you cannot observe the string, yes. What makes you think of maybe the atoms is actually a string? What kind of phenomena makes you think of?
Good question. In other words, you're saying, and I should have emphasized, that we don't have experimental observation of strings yet. So we have not seen actual strings in the laboratory. So what makes us so sure that they exist? The reason we think it exists, we cannot be 100% sure because we have to ultimately see in experiments. The reason we think it is the case is that over many decades, people have tried to understand quantum aspects of gravity, and it hasn't quite worked. Strings automatically give you answers which are finite and make sense with gravity. A very surprising, rich structure. We don't believe such a rich structure exists without it being true. More than that, it incorporates all the physical pieces that we think it should be there, like forces, gauge forces are there, unification of them with gravity is there. A lot of these features are there. So both aesthetically as well as connections with what we already know suggest that they exist. But of course, experiments are the final judge, and we have to wait.
Okay, thanks very much. Let's thank Professor Vafa once again. And next, let's welcome Professor Leslie Valiant. To the stage. Yeah.
Well, good afternoon. So, thank you very much for inviting me, and thank you, Professor Yao, for the very kind introduction. So, my topic is similar to the previous talk in that it's all based on mathematics, but it's different in that what is studying is not the physical world as the kind of intellectual world, the world of computation in the brain and in living things. And I'll talk mostly about this one recent book I have, but I've worked generally in this area for a while, so I'll mention briefly that two previous books, and writing books is a lot of effort, and there are various reasons why one may want to write books. So the first one was like an academic monograph. I just wanted to write down my thoughts on something which I believed was new, and writing a book gives you quite a bit of latitude in writing what you like. So I enjoyed that. So the second one, probably is related somewhat to what I'm going to talk about. So that was about machine learning. So this was partly a book to popularize some ideas which had existed in the literature by then, mostly in papers. And so, as I say, it was about machine learning, but just have one line from the book. So just to give you some idea of what machine learning is about. So this was published about 10 years ago, before machine learning became so popularized with large language models. And I try to introduce these two words, theory full and theory less. And by theory full, I meant areas like mathematics and physics, where there are some rules, and you can argue, and you can draw conclusions, and there's a theory, and if you put together some facts which you believe are correct, then you get something else which is correct, so there's a theory. And of course, there are other things which have theories which we deal with, like a sport. So a sport has rules, so you can argue about the rules of a sport. And the laws of a country, there are rules, you can argue about laws. So there are these various areas where we're used to logical thinking, like the mathematical sciences. But I was drawn to attention to another area of the theory less, the idea that humans are also capable of doing some things with very high accuracy, even though we don't know exactly what the underlying rules are. So, for example, we are very good at recognizing if someone shows you a picture of an animal, you can recognize whether it's an elephant or not, and we agree to a high degree, so we're very skilled, but we don't know what rules we're applying, so that's the theory less. And maybe the application which we've all seen recently with large language models is being able to compose smooth sentences, say in Chinese or English, so you can write text, very smooth text, flowing text, valid, grammatically valid text, although in fact we don't quite know what the rules are of the game. And these kind of behaviors are all, my hypothesis was that they're all produced by some sort of learning process where you learn by example. And of course this is exactly what large language models do. They're given lots of sentences from a natural language, and they're trained to predict the next word. Okay, so this kind of learning will be a topic of my next book, which, as advertised, is called The Importance of Being Educable. And I'll try to describe various aspects of what the book tries to do. So one question which I think the book gives an answer to, it wasn't my intent in writing it, was to give a simple view of what current AI is, because the view one gets from the media can be very confusing, and it is confusing. But by looking at the question more generally, one can get a simpler view. But the problem which I'm looking at more directly in this book is what is the cognitive capability there's a word missing there, that humans have that have enabled us to build this civilization that we have built. So what is special about humans which other animals do not have? And this is very similar to the question of what is the potential power of AI, since in AI we essentially ask machines to do things which humans are good at. We always ask computers to do things which we want to do, we wish we could do, very close to human capabilities. Okay, so as I said, so here we're exploring the world of thinking, and the person who first showed that this area could be studied using mathematics was Alan Turing, and he also gave us a license to talk about humans and machines in the same argument. Okay, so he asked, can every task done by humans be done by a machine? So this was a question which everyone asked in his day, and also everyone asks here today. So in a radio broadcast, he famously said that it is customary in a talk or article on the subject to offer a grain of comfort in the form of a statement that some particularly human characteristic could never be imitated by a machine. It might, for instance, be said that no machine could write good English, or that it could not be influenced by sex appeal or smoke a pipe. I cannot offer any such comfort, for I believe that no such bounds can be set. And the interesting thing here is that this wasn't just a philosophical opinion, but this followed from his main science, which came to be known as the Church-Turing thesis, which is that a mathematical model of computation, what became called the Turing machine, is the most powerful kind of mechanism for computing in this universe, including methods of computation by biological, physical, chemical, or whatever mechanisms the world offers. Okay, so this we should take seriously, and I think this we should regard as kind of settled. I should note that there are some philosophical issues which people raise, but these are philosophical. So I think, for example, his reference to smoke a pipe, I think is some kind of philosophical joke, I think, because obviously he did not mean whether you could make a machine which burns tobacco. He presumably meant whether you could make a machine which enjoys smoking a pipe as much as a human does, whatever that is. But these things of perceptions, feelings of computers and humans, these are very hard to discuss with science, and we won't. So we want to discuss behaviors which are externally visible. So, so what I regard as unsettled science, which he didn't settle, so he said machines, humans, the same. But what he didn't say is, well, what are humans and what are machines? What are humans capable of? If we can't say that, then where are we? So how do we characterize what human capabilities are? And we seem to be amazingly bad at this, amazingly. We've studied humans for thousands of years, but we don't have good answers. So, for example, what about human intelligence? I think most people, as a first guess, would say that what's special about humans, what distinguishes us from other animals, is our intelligence. And in fact, we are very obsessed with this. So when we measure our mental abilities, we call the result an intelligence quotient. When we attempt to emulate our mental faculties, we call it artificial intelligence. Some fear that machines more intelligent than humans would be an existential threat. And in searching the cosmos, we are seeking intelligent life. So you would think that we really understand intelligence if we keep talking about it, but we don't. So even the experts don't. Some expert psychologists were asked to define what intelligence is, so we really knew what intelligence tests measure, but they concluded that when 24 prominent theorists were recently asked to define intelligence, they gave 24 somewhat different definitions. So we don't know what intelligence is. And this is consistent with history, that intelligence in the sense of intelligence tests were originally defined not by saying this is how you recognize an intelligent person, but saying that many different tests you do, some people are good at many things, some people are bad at many things, and somehow the correlations between how well you do in many things is your intelligence. But this is a very indirect thing. You would think that we deserve better, that we somehow, if we're judged on whether we're intelligent or not, someone should tell us, what are we supposed to do? So I'm interested in more explicit definitions of our human capabilities. Okay, so this is back to the book. So I'm just summarizing the cover designers. So books have cover designs. And so the question I'm asking is, what is the cognitive capability that enables humans to go from this primitive computer cursor in a rather short amount of time, a few thousand years, in a period where no one believes that there was significant biological evolution. So it must be that we have some cognitive capability. At the first stage, we just took a long time to kind of come to fruition and create the civilization we have. And the question is, what is this capability? Okay, so I call this the civilization enabler, this capability which enabled us to go from one to the other. And so this isn't a total theory of humans, or even of, okay? So we can leave out many things which we share with other animals, however interesting or complicated they may be. So vision, how we see, how we move, locomotion, our emotions. I mean, all these things are very widespread in the animal kingdom, and what's special about us is not any of these. What's special about us is some more higher capability of processing information in complicated ways. And so the methodology, inspired by Turing certainly, is computational. And very briefly what this means is that when I say that we do something, we're capable of something, I want to define it as a function, as an input-output thing. So if you can do something, I want to know what's the result afterwards, which was different from what things were before. So defining what the changes are when you execute your talent. And the second notion is computational feasibility, that if I attribute to you some capability, it shouldn't be some abstract thing which is impossible to do in the universe. It should be something which is realizable in a feasible number of steps. Okay, so this question of what's special about humans has been asked by many academic communities for a long time. Of course, I have a website here where you can look up 617 different topics which academics have studied, in which humans and our closest relatives differ. So which one is the civilization enabler? Again, it's a capability we have which enables us to achieve this civilization we have. So eyebrows are supposed to be unique to humans, but they're not a capability, and there's no theory which says that if you have eyebrows, then you can build a civilization. Similarly, many other things were important in human history, like animal domestication, but again, there's no theory which says that if you can domesticate animals, then you can build computers. So the many other things have been suggested to be special to humans, like collaboration, social learning is learning from each other, intelligence, as I said, not well defined. So symbols and language, so they're getting closer. I'll say more about them in a second. But again, so language isn't a candidate because it's kind of, well, A, it's not really a capability in this sense, but also if you teach an ape language, it doesn't make it want to do advanced things. It doesn't make it make it want to build a rocket to go to the moon. Okay, so it doesn't. This capability isn't enough to make to explain things. So this question of civilization enablers has been asked, especially since the time of Darwin. And so his view was that, among the different candidates, like the ones I enumerated, none of them is a strict explainer of human uniqueness. He thought that in all these dimensions we differ only in degree from other animals. Okay. So what are we doing here today? What does this book do? Well, the main idea is that with these computational notions, I'll define these tasks slightly more precisely using mathematical notation. And because I'll define things more precisely, I can define things slightly more complex. Okay, so if in Darwin's time all you could do is to look at single words in the English dictionary and say which of these is the right civilization enabler, then maybe he was right that none of them was an explanation by itself. But maybe with more precise language we can express some more complicated idea. So maybe we need a more complicated idea than simply a word already available in the language. Okay, so I can briefly tell you what my proposal is. So basically in the book I have a proposal for this capability, and then there's a list of different directions in which one can go if one believes it. Okay, so if one accepts that this is what's special about humans, then there are various consequences. So I'll list those as well, maybe rapidly. So this capability, which I say is unique to humans, I call educability. So it's a definition. It's a compound concept. So as I'll say, it's made up of 3 or 4 different components. So I think that's the complexity it needs to have. So it reminds me of the human capability to be educated, by which I mean something very general, that all the time people look at their cell phones, they read novels, they watch movies, they're all the time trying to take in information. And we can not only take in information, but we can kind of process it, we can associate it with other things we already know, we can use it. So we seem to be hungry for information. And of course formal education forms a big part of human activity. So I'm saying this kind of activity is very fundamental to humans, and I try to spell out what it is in concrete terms. Okay, so I'll give you a quick definition, then I'll say slightly more precisely what they involve, and then I'll go on to some consequences. So the first capability is what I call acquiring beliefs by generalizing from experience. So by this I mean exactly what one talks about in machine learning as generalizing from many examples. So this is what basically current AI does, and does very successfully. But it's a very specialized thing. It's not everything. It does one thing very well, it's very useful, but it's not everything, and that's why we have to move beyond it. So basically, what I mean by this is what I meant before by how we deal with the theory less, that we see many examples of something, like examples of pictures, and some are of elephants, some are not of elephants. Somehow we can figure out, from this we can learn how to recognize elephants in the future. So the second component of my definition is that once you have learned to learn these beliefs, you've learned to recognize elephants and many other things, then surely it would be a waste if we couldn't combine these beliefs, so chain them together. Okay, so if you're planning what to do, how to get home this evening, then you may make the first step, then the second step, then the third step, and each part of your plan is applying something you've learned, and you're applying it in sequence. Okay, so this is a very natural thing to do. And the third thing is more to do with very traditional education, which is that we can also acquire beliefs by being told the belief explicitly described to us by others. So by belief here, I mean anything like a recipe, a formula for doing something, a prescription, a computer program. So someone explicitly tells us how to do something, and we just execute it. So it's not based on our experience. So this may be a formula you learn in a physics class, which other people have discovered from their experience to explain some physical phenomenon. But you don't have to repeat the experiment. You're just told the formula, and you have all the benefit, which the poor guy who had to do all the experiments acquired at great labor and cost. Okay? So I'll go through this again in a second. So all this has to be in a context which is rich enough. And by rich enough, I mean that all this knowledge can be applied to what I call a multi-object scene analysis, which means that when you look at the world, you don't just look through it through one pixel, which is light or dark, but it's a richer world we see. You may see in front of you, say, 4 people. You see who's sitting next to whom, and some relationships. So we can examine the world at some detail. And the last aspect is that we also can do symbolic naming. So for individuals, for scientific concepts, we can dream up an arbitrary name for it and then use it to refer to it. I suppose when you call a dog by its name, that's the beginnings of symbolic naming, because you can call your dog anything. Okay, so that's basically the definition. And so educational philosophers talk about many things, but they usually make contact with these things. So certainly number 3 is very traditional education, where you listen in a classroom and someone recites some facts or theories. Number 1 is more hands-on learning, where you do some experiments yourself. And number 2 is that you apply what you've learned to specific situations. So I think most people think that a good educational experience should have some element of all 3. And so these are formalizations of all 3. Now, if you're interested in human evolution, you may want to guess, well, when did humans acquire these capabilities? As I said, it's multiple. And so this is just a guess. I don't need to guess a timeline, but here is one. So certainly, generalizing from experience must be very ancient. So every animal does it. When the most primitive animal in the ocean looks for food, it learns from experience where to find the food. And certainly, if it learns things, it will also combine it. So the aspect which is most recent, the most recent addition, is the last one, that we can follow instructions given to us by others. Of course, for humans, this is done mostly through language. So in fact, most of the things we do, knowledge we transfer to each other, would be hard to imagine without language. But in principle, animals can also be taught complicated things by demonstrating physical things. So it's believed that our species is about 300,000 years old, and so a reasonable guess is that our basic capability came together before our species emerged, merely because people have searched for biological changes in humans in the last 300,000 years, and nothing amazing has been found. So it's not conclusive, but it's quite possible that we started with this capability, and it just took a very long time for this capability to become so useful. It's like a snowball rolling slowly and becoming bigger. As our knowledge increased, it became more and more useful to gain more knowledge. Okay, so so very quickly I'll go back to through the three components. So generalizing from experience is I identify with the classical picture of machine learning by example, which is that you have some learning algorithm, and it takes examples with their labels, so maybe pictures labeled according to the species according to what the picture shows. And then this learning algorithm generates a classifier, which is another algorithm, and the other algorithm will then classify new examples according to the label. Okay, so this is classical machine learning. And as we know, if you do machine learning, is that it's important that where you learn from, the world in which you take the examples should be the same in which you test your classifier. That if you learn but the world changes too much, then what you've learned isn't useful. So to make this model more concrete, so this is probably approximately correct model of learning, whose main feature is to give a quantitative constraint on what you need to realize before you declare your machine to be really learning. And the constraint is that the accuracy of predicting new examples should increase, so the error should go down as you've put more and more effort into the learning. Okay, so maybe you learn from 1,000 examples, 1,000,000 examples, 1,000,000,000 examples. As you learn from more examples, you have to do more computational steps. As you put in more effort, you should be rewarded by being able to classify in the future more accurately. And in particular, this requires that the reward, that it goes down fast enough, error decrease fast as some sort of algebra law, which in more concrete terms means that if you increase your effort 10 times and you halve the error, then when you increase the error another 10 times, you should halve the error again. So this is like an adequate reward for spending more and more money on training these nets. Okay, so this is learning from example, and this is, as we know from experience, this is a powerful way of doing this. So second part was training beliefs, and here the phenomenon is that what we're training are these classifiers which we've learned, and these classifiers will make errors. Okay, so when we chain together things which make errors, we have to be careful that the conclusions we draw are not nonsense. Okay. Now, this idea of combining uncertain things has been discussed, but not that much. So just to give a quotation from the world of politics, actually Winston Churchill may or may not have said this, I'm not sure whether he did, but he said, true genius resides in the capacity for evaluation of uncertain, hazardous, and conflicting information. But I mean, what I want to emphasize here is that I mean this almost ironically, in that dealing with hazardous and conflicting information is what every little animal has to do from the start. So life is full of dealing with avoiding predators, etc., etc. So having a principled approach to combining uncertain information is something which is kind of a very essential part of life, and in the system one gives it a first-class status. And so I've got a system called robust logic which does this. It's not like standard logic, it deals with facts which are uncertain, but it's got an analog of soundness. So soundness in logic means that if you combine two things you're sure of, the conclusion should be sure, as long as the method of combination is in your rule book. And again, it should be computationally feasible. And very roughly what this corresponds to is that in In the standard learning scenario, we've got one big box. This is a supervised learning box, as in what I started with. And in this robust logic, what we'll do is we'll learn many boxes. We're still going to learn many things. Maybe you have a separate box for each word in the Chinese language. And then when you look at something, some of these boxes will say, yes, these words are recognized. And then you can chain together conclusions through these different boxes to reason, to reach some complex argument. Okay. So the standard back learning gives you guarantees for generalization, and with this you also get guarantees when you chain together different things you've learned. And very basically, for example, if you got two rules which you believe to 99% confidence because they're really supported by the data you've seen, then when you chain them together, it may be reasonable to expect 98% accuracy in the prediction. So you want some lower bound on how reasonable it is to combine information. Okay, so as far as what complexity the world has to be described with, so this is some crow, a clever bird, which is given some experiment to do. They're very good at figuring out solutions to hard puzzles. So here it's something like you've got a glass with some water in it, and there's a seed floating on it, and the bird figures out that if you put stones into the liquid, then the water level will rise, and it'll be able to eat the seed. But the point is that this scene has to be understood by the crow to some detail. And so, for example, the fact that there's a glass is one object, the water in it is something else, there's a seed, there's a water level, the water is in the glass. So all these basic relationships somehow has to be in the a bird has. So there has to be some richness of description of the world for any of this to make sense. And okay, so this is just an illustration, a different illustration. So how this works is that, so maybe the system, okay, so these dark circles are called tokens here. So when you wake up in the morning, you may think of your dog, and you may also think of the relationship that your dog likes something, and you may wonder what your dog likes. And how you'll solve this problem is that you bring up from your mind you conclude it's a bone, but how you'll do this is that you will bring up in your mind a classifier which predicts what that object is. So a classifier which predicts bones or not bones will be the one which tells you that this missing object is in fact a bone. So how these things work is that using machine learning, you're going to learn maybe a rule which predicts bone, and the rule will in fact be a classifier. So if you like deep networks, this will be a deep network. If you like some other representation like decision trees, this will be a decision tree. Okay. But the idea is that in your mind's eye, you have this picture, your dog likes a bone, and then maybe you predict the next thing by using another rule. So this is how in our imaginations we can make plans and we can make deductions by giving partial information and applying what we've learned in sequence in a chain. Okay, so for a situation in mind's eye, you chain the applicable learned rules. Okay, so just one example, especially for people who like machine learning. So if you ask a human the question, did Aristotle own a cell phone? Most humans can answer this correctly in a fraction of a second. But this question doesn't look like a good question for a pure machine learning system, say based on information on the internet, because there isn't very much information about Greek philosophers and their personal possessions. Okay, it's not what's listed on the internet. Okay, so obviously we solve this by doing some sort of chaining. We have some information about when Aristotle lived, when cell phones were invented. We chain things. So the theory is that we solve this by doing some sort of chaining and reasoning, and we can put this on a theoretically well-founded basis, but this is beyond the simple machine learning paradigm. Okay, so let's go on to the next thing. So the last component of this educability was taking instruction from others. So what this amounts to is that given everything I've described, if someone else has a belief in their heads, they can just tell you the belief and you'll know it, you'll be able to execute it. So you can receive explicit beliefs from others, and mathematically this is just like a universal Turing machine. Okay, so educability is the realization and integration of the capabilities I've described so far. And just to summarize the benefits of this last thing, which are kind of the obvious, that if you can tell people your discoveries, then they don't have to go through the painful process of doing them. And in fact, one person can tell 1,000 people their discovery, saves 1,000 people from discovering themselves. Also, some of the discoveries people make are very powerful discoveries, which are methods of reasoning. They're not just arbitrary facts. So, for example, arithmetic, someone must have discovered, and without arithmetic, we couldn't do very much science. And this is, again, arithmetic is something which we teach each other. So the accumulation of science with contributions from thousands of individuals, that all needs this part 3 of what I'm saying. And this has enabled technology to become so broad, go to the moon, build computers, cure disease. And also, we have complex human cultures. So as a diagram, the idea is that we live in a complex environment, and basic machine learning, back learning, and reverse logic are all about adapting to this complex environment. And in some sense, if your environment is stable and you've learned where to find food, then you're safe to go and find food the same place tomorrow because the environment is stable. But when you go on to acquiring programs by instruction, so if someone tells you something in a lecture room, is that safe? I mean, how do you know it's useful? How do you know it's true? Of course, all this is in an education system. This is all based on trust, which is necessary. But once you acquire beliefs from others without having seen the evidence for it, so in the first two things you see the evidence, and for the last thing you don't see any evidence. You just have to take someone else's word for it. So okay, so I'll just now quickly describe 6 differences, which, if you take this theory seriously, this may make. And the first one follows what I've just described, that the fact that we're so educable, we can pick up information so fast in the ways I've described, is very good. But the third aspect is dangerous in that we can pick up recipes, formulae from others, facts or pseudo-facts, without being able to verify whether they're true or not. Okay, so then we're easy victims of arbitrary belief systems, ideologies, conspiracy theories, misinformation. So the idea is that I've described lots of ways in which we can process information and acquire it, but I haven't described any way in which we can verify whether what we've learned is true in the world we live in. So I think it's a fundamental problem. There is no way in which we can verify the truth of something, but we're told what what the result of an experiment is. We're told what happens on the other side of the world. We're in no position to verify it all. We have to take it on trust. But in some sense, we have to recognize that this is a basic weakness we have, and we may benefit from recognizing it. Okay, so a different direction. It would be great if we could improve our educability. What if we could learn faster, etc. So how do I improve my educability? Well, this question only makes sense if we can measure educability. So sub-question is, what would the test for educability look like? And in some sense, the answer to this is the simplest thing I'll say today, because a test for educability wouldn't test for your previous knowledge, it wouldn't test for your previous traits, it would only test how well you use knowledge which you've gained during the test. So the test starts now, you will be given some information, and then you will test it on how well you've acquired the information, how well you can generalize from it, how well you can reason from it, whatever. But this wouldn't be a test for any skill you already had or any knowledge you already had. The only skill would be a test of educability. So in some sense, this is an extremely simple idea, and it may be hard to realize in a pure sense, but it's a very simple ambition. And for example, typical IQ tests like if apple is to seed then, this doesn't test educability because I haven't told you anything new. I'm testing you for your previous understanding of some relations. Okay, so this is not what we want. Okay, so next I want to emphasize that educability has many parameters. So mathematically, this is a downside. We like mathematical models which are very clean, but here it's the opposite. And so, for example, if I have a standalone system, which is educable, intelligent, machine learning, whatever, then one fundamental question is what is its belief choice policy? So does it believe everything it's told? Does every labeled picture? Does it believe even if it's contradictory? So we know that humans have quite sophisticated ways of deciding whom to believe. So children believe their parents first, later on maybe they believe other people, we believe people in authority. But so this is a parameter of any machine which is in any sense educable, and in this sense already there isn't a unique best way of doing anything in this area. You've got choices of what belief choice policy you have and of many other parameters, and this is a feature of, I think it's, so having many parameters is not a bug of this concept. I think it's a feature of cognition that, we're all different, we're good at different things, we have different knowledge in our heads, we're very incomparable, and I think cognitive systems will be incomparable in a similar way. Okay, so singularity. Some people worry that ultra-intelligent machines will seize control of the world and treat us like dogs. So I don't worry about this so much. In fact, not at all, because these arguments are usually based on some mystical notion of intelligence, which is not defined. But if we define capabilities in this very prosaic, understandable components, so what I've described, you learn from examples, you chain things together, you do some universal Turing machine stuff. It's all very prosaic, so why be afraid of that, even if machines can do it faster and on a bigger scale than us. So, for example, it's possible that all there is are the capabilities I've described. Maybe there are more, but supposing there are only these, with all the parameters that machines will do these very basic kind of tasks with many choices. They'll make many choices which has to be made in their design, and they'll all be different, incomparable. Maybe they'll do everything faster than we can, but we shouldn't. It doesn't seem to be such an existential threat anymore if you spell out what these capabilities are. Okay, with studying human behavior, social science theories are different from, say, physics in that there are usually many different approaches. Also, sometimes social scientists are believed to have gone badly wrong. So 100 years ago, the eugenicists thought that nature was much more influential than nurture, and they gave the emphasis they gave to nature over nurture was much bigger than we would now. And generally in social sciences, the difficulty is to draw conclusions about human behavior that are transferable in time and space. So generally so I'm supplying here a word educability, and basically what educability does is to give a word and some mechanism for nurture. Okay, so when we say that human nurture is so important, well, what is nurture? So exactly in what way are we influenced by our environment? And so educability is an attempt to spell out some ways in which our environment influences us, like we believe what we're told. The examples we see, we generalize from. Lastly, education. Well, clearly there are links with education. It would be nice to have a more scientific basis for education than we have. So education, I think, is mostly based on best practices endeavors around the world. So, of course, some people do study systematically, like what's the best way of teaching reading by doing surveys and trying different methods. But one would think that if we studied the basic processes by which we acquire information, then maybe we could say more about education. Okay, so thank you. I'll stop there.
Thank you, Professor Valiant, for this fascinating talk. Questions now from the audience? Yes?
Hello, Professor. I want to know what preparations should middle school students make to embrace the upcoming era of comprehensive artificial intelligence?
What's the word you used before artificial intelligence?
Comprehensive.
Comprehensive. Well, I think a big question is what is comprehensive artificial intelligence? So in some sense, this educability framework, I think, is one suggestion for what artificial intelligence can be, which is realizing these capabilities. So I think I find it very hard to answer your question because artificial intelligence, machines being able to do these things very efficiently, will cover all aspects of our lives. It'll cover everything. So whatever you do, you probably have to anticipate that machines may be there to help you or hurt you. So I think you need, so I don't think there's a general answer. So I think in whatever particular area of activity you're interested in, you'll have to, you can't ignore AI. That's what I would say.
Hey. Other questions? There. So, who wants to ask? Yeah. Maybe we'll let the...
Hello, Professor. I've noticed that in machine learning, the computer usually takes in like a large set of data, but conversely, as for humans, we can make generalizations or we can extract theories from a rather small set of data. So how is that? So in your point of view, is it possible that through some type of like mimicry for the human brain structure, or through other type of more efficient algorithm, that one day the machine can take in a set of data that as small as necessary for humans and still make valid generalizations and inferences? Thank you.
Yeah, so that's a great question. I think the situation now is that standard machine learning is very successful, but people make the mistake of equating that to AI. People take it too seriously. Okay, so what I'm suggesting here is that we're capable of we have a series of capabilities, one of which is generalization, and if we exercise these capabilities together, then we can do as many things we do. So, for example, there are also capabilities I haven't described because I think other animals can do it as well, like recognizing an individual. Okay, so the fact that I can recognize an individual is different from generalizing from many examples, and I can do it on one case, but other animals can do it too. So saying that we recognize individuals by doing generalization, that would be a mistake. But I think the one example I'd draw attention to is my example about Aristotle and his cell phone. So this was a case which I suppose you couldn't learn at all from examples with standard data sets, but you can do with reasoning. So I think many of the phenomena which I think you allude to that we can do with few examples, we do by having previous knowledge and using reasoning. Okay, so I think you have to use these different capabilities together to get the phenomena we find in human performance. And it's a big mistake to think of just vanilla machine learning as being everything. It's not. It's very, very powerful, but thinking of that as being AI is wrong.
Right. So deductive reasoning has played a huge part in like intelligence as well as
Exactly, yes.
Thank you, Professor.
Okay, does this answer your questions as well? Okay, maybe you let you ask also.
Hello, Professor. I want to ask that if we can enable AI to have the same mechanism as we think. In other words, can AI think like humans? It could be AI could have a larger about it, about everything. So can AI think like human and help our science development? That's all.
Yeah. So could someone summarize the question in one sentence?
It's about that can AI think like humans and help our science development?
Can AI think like humans and help?
Help the scientific development.
Help the science. Well, I think I think AI and humans, I believe, have fairly more similar thought processes. AI can have similar thought processes to humans, and I think they can help. Will be able to help scientists. So at the moment, they're helping scientists just in the way of standard machine learning because that's what's being implemented. But if kind of reasoning is added to these learning systems, then I think the machines will be more useful in helping humans in the sciences. But they already are very useful because powerful application of just generalization, like in protein folding, is very powerful.
Okay. Other questions?
Good afternoon. I have a question. However, with the with the rapid development of technology in the context of the continuous progress of artificial intelligence, it is possible for humans to overlay omissions and external information, thereby gradually weakening this unique ability of this urn.
So can you summarize the question?
Yeah, right. That's what I want to do, yeah. Yeah, so basically you emphasize the importance of abilities such as generalizing from experience, training beliefs, and accepting instructions from others. However, with the rapid development of technology, especially in the context of the continuous progress of artificial intelligence, is it possible for humans to overly rely on machines and external information, thereby gradually weakening these originally unique abilities of their own?
Oh, I see. Okay. So, yeah. So, do we become stupid if we rely too much on machines? Yeah. Well, you know, who knows? Obviously, if we push things to extremes and we don't use our brains at all, then all kinds of things can happen. But personally, I'm not afraid of that. I think we'll always use machines to simplify some things which were previously complicated, and I think we usually move on to then do other things with our brains. So I think what you're suggesting could happen. I can't prove to you it won't happen, but personally I'm not so worried about that. Okay.
Yes?
Hi, Professor. I'm a student from high school affiliated Renmin University of China, and I'd like to ask a question. Like, for future, AI might be able to help experiments and explore physics, but sometimes for the equations, as the previous professor has said, equations are not very precise, and also the data is not precise. So might there have a very big mistake and error for the model to build, and thus cause mistakes for the results that AI have produced for scientists to discover the future?
In your question, so what is the source of error? Is the AI the source of error, or experiments?
Like the AI, would AI cause big mistakes due to error for scientists to produce and explore physics in the future?
Yeah. So you're worried about the AI systems making errors?
Yeah, she was also referring to the previous talk where basically you can have a phenomenon which apparently, given a few data sets, seems to be following a certain law, but it's actually not, and the AI might extrapolate from that and do some huge errors. Yeah, is that correct?
Yeah, but I mean, the AI would, I'd guess, would make similar mistakes to humans. So from the information I have, it's not obvious that the AI would make more mistakes or less mistakes than humans. Okay, so I mean, the main thing for AI to do, I think, the main program for AI scientists is to make AI more trustworthy. So if the AI isn't trustworthy, if it's unreliable, then that's terrible, and you shouldn't trust it. Okay, but so I think that's what I think is important. That with AI, the trustworthiness of the system is critical, and the users will know. I think if you use a system well, you'll know how trustworthy it is. But
so it's important for AI to help scientists produce the theory and use scientists to do the experiments to prove the theory that they are reliable and correct?
Well, I think the AI should be used in wherever it's useful. But I'm saying that if you've got special concerns that the AI is unreliable, if that's your main concern, then I mean you're correct in having that main concern. Everyone should have the same concern, but the result will be that AI systems will be developed which are more reliable and more trustworthy. And people who use it will know exactly how much to trust it.
Okay, thank you very much.
Okay, so I guess we just have time for one more quick question. So,
hi, sir. I have a question about human and AI are quite similar, and so it can learn with acting and living. And while AI is like, first we need to train it, and we can predict that, and it's a separate two thing. But in human, it's only like mixed together. Yeah. So is there any possibilities for AI to train like humans? Like we can learn by experience, and also we can adjust the parameters to make the AI model predict better, and during the development and in actual exercises.
So can you summarize the question?
Yeah, so you basically say whether the AI can learn more like a human by also doing, by developing in a similar way in an environment. And not just data, but then also undergoing some development, some other situations. Is that correct?
Yes, so I don't see any reason against it. So you'd, like we are, it would have to be a standalone system which just stands there, and it'll have to have these parameters which tell it how to update itself, where to find new information, and the kind of things which humans do. So in principle, yeah, I don't think there's a fundamental limit to that.
Okay. Thank you very much.
Thank you.
Okay, so yeah, let's end the question and answer session at this point and have a short break. And let's thank again Professor Valiant for the wonderful talk. Okay, so please take a seat, everyone. We will start with the next part. And I'm very happy to welcome Professor Hiroshi Oguri to the stage, and he will be giving his presentation. Thank you.
Thank you very much. So I guess my talk is about 15 minutes, I think, and so it's until about 5:20 or so. I was asked to give. So this is. I was told this is a book introduction event. So I thought I should introduce my 5 books that was published in China. So these are 5 books, and I thought I would tell you a little bit about some of the books. I just met a publisher that published these 2 books. And they say that those sold over 100,000 copies in China. So thank you very much. And so this is our first book. It is Gravity, published in 2012, and in China 2015. And this movie actually inspired production of movie that we're going to show tomorrow. And so about a month after this book was published, I got a phone call from the publisher saying, check out Amazon. So I went to the Japanese Amazon site, and it was actually #1 book on all the books sold in Japan. And it was actually sold more than the book about how to lose your weight, or the collection of photographs of young singers. And so at just a few hours, Japanese people care more about what is gravity than looking at the photograph of young Japanese singers or how to lose weight. And this book was published after Higgs boson was discovered at CERN, trying to explain the standard model of particle physics. And this is actually a book about superstring theory, discussing more detail about superstring. And I'm honored to have received some popular science book award in Japan. And this book is about mathematics at the level of high school student. And this has been adapted for introductory course in several universities in Japan. So maybe Chizen College can use this, maybe, I don't know. And this book is about called The Spirit of Inquiry in Japanese. And this is actually a different flavor. This is not really a popular science book, but half autobiography and half about the importance of basic science in society. And I'll tell you a little bit about this book later. Okay, so I would like to tell you about some of these books, and I thought I should first focus on this book, What is Gravity? And this is a photograph I took about a few days after this book was published. I was so tense in publishing this paper, so we took a vacation in Jordan and went to a Dead Sea, and you can see me being confused about what is gravity. This is a Japanese version of this book, What is Gravity? You see, I'm very confused about what is gravity floating on the Dead Sea. And so when I started writing this book, I thought, well, how to sort of introduce the concept that gravity is a very mysterious thing. Because everybody thinks that gravity is a very familiar thing that you feel every day. So I thought that first I would like to tell the reader that there is something very mysterious about gravity. So in fact, as I wrote here, the gravity is the most familiar force. We feel that every day. We can measure it in weight measurement. But it's also very mysterious, and it actually holds the key to some of the deepest secrets of the universe. So I wanted to explain this. So at the beginning of the book, I started with discussing 7 wonders. So, of course, you might have heard about 7 wonders of ancient world. So this was like a guidebook in the ancient Mediterranean. So there are various mysterious sites like Hanging Garden in Babylon, Pyramid in Gaza, or lighthouse in Alexandria. And so mimicking this, I started my book discussing the 7 wonders of the gravity. So I thought that in lieu of the introduction of this book, for the next 30 minutes or so, I will tell you about the 7 wonders of the gravity. So the first wonder is gravity is a force. Now, if you write it in Chinese, this is like a contradictory statement, because you already have the word force in your, when you spell the word the gravity in Chinese. But it was not obvious for many, many years that gravity is actually the force. For example, this is Aristotle. Aristotle showed up in the first two speakers also refers to Aristotle, so I also refer to him. And for him, in fact, he didn't think of gravity as actually a force. he thought that, well, everything is made of 4 elements: the earth, fire, water, and air. And everything that's made of earth tend to pull towards the center of the earth, because that's where originally the earthly objects were. And this was more economical way to explain the gravity, because mainly when we feel gravity, we feel that towards the downward. So this was easier to explain in this way. And where in some sense science is economic of thought. The most economical way to explain things is better. So in some sense, this is the better way to explain gravity at that time. So if you ask what the forces are, you should ask, well, we need a definition. So we are scientists, so we need a definition of what the force is. So this was actually discussed in the morning, actually, during a panel discussion. But I think it was actually Isaac Newton who defined the force. And he defined the force by his famous equation. The mass times acceleration is the force. In fact, you can think of this as the definition of the force. The force is something that changes the motion. So if you don't have the earth and the gravity, then the soccer ball would go straight. But if you throw a soccer ball near the earth, it gets bent. And this shows that there is a force there. That's sort of the definition of the force. For the last 10 years or so, as our science progressed, we have discovered more different kinds of forces. And during the 20th century, we discovered 2 more kinds of forces. In addition to our familiar gravitational force and electromagnetic force, we discovered strong and weak forces. And the strong force works to combine quarks to make protons and neutrons. And weak forces are responsible for radioactivity and how the sun shines, etc. So these are like new kind of force that were discovered in the microscopic world. And now we understand these 4 forces, but there is actually an order in these forces. Strong force, as the name suggests, is very strong, and the electromagnetic and weak. And interestingly, the gravity is the weakest force in nature. So the second wonder of the gravity is that the gravity is the weakest force in nature. And this again sounds a bit absurd, that the gravity is the force that feels most strongly in daily life. Basically, after all, that this is a force that actually throwing us into the universe. So why do I say that gravity is weak? So here is an experiment one might consider doing. Supposing here I have some kind of iron clip, and then suppose I have a small magnet, and I approach it to the clip, and at some point the clip jumps to the magnet. And if we think about it, this is surprising because Earth is actually billion times billion grams. And the gravitational force from such a huge object is weaker than the magnetic force from the very small, tiny magnet. So that sort of shows that how weak the gravity is. Another way that we say that gravity is weak is, for example, I'm standing here. Even though the gravity is pulling me downward, I'm able to stand on this podium and does not go under the ground. Why is it? Because I'm made of electrons and atoms, and the floor is made of electrons and other things, and electrons repel each other by the electromagnetic force. And that repulsion is stronger than the gravitational force, and that's why I'm not going down under this podium. Okay, so this way we see that the gravity is actually the weakest force in nature, and this is in some sense very surprising thing, and I'll come back to this point later. Okay, so another surprising thing about gravity is that we can make it disappear. Okay, do you believe we can make gravity disappear? So here is, for example, the photograph that gravity disappeared. So here is Stephen Hawking, who is, of course, famous in his research of gravity. But here he is in a situation where his subject of study disappeared. And the way this photograph was taken is that you have this airplane that you don't see outside, and then you go up, and then suddenly the airplane turned off the engine and start making free fall. And then for a few minutes, you can be in this situation. So you can turn off the gravity in this way. And this was actually noticed by Albert Einstein. He thought that when he came up with this idea, he was still working in the patent office in Bern, in Switzerland. And he didn't have the faculty job. And but in some afternoon, he realized that for an observer falling freely from the roof of a house, the gravitational force does not exist, just like this. And he called this as the happiest thought. It actually led to his discovery of general relativity. So this goes on, this takes me to another wonder of gravity, which is that gravity is a warping of space and time. And so he noticed this idea that you can turn off this gravity by falling, but it took him 10 years to turn this happiest thought into general relativity. And one of the reasons was that mathematics in formulating this was so difficult, and in fact at that time very advanced. But in order to understand this, you also have to rethink what is time, what is space. We need to rethink about this kind of everyday notion. So coming back to Aristotle, Aristotle famously said that nature abhors a vacuum. And this is not a trivial statement. This is not to say that it is actually difficult to make a vacuum. Of course, to make perfect vacuum, it is very hard. But that's not what he meant. What he meant was that space and time does not exist independent of matter in them. So it does not make sense to consider abstract space and time without any matter in it. That's what, so somehow he thought that space and time and matter are intricately related to each other. This point of view was changed by Isaac Newton, that in order to formulate his laws of motion, he postulated the existence of absolute time, independent of matter, which flows uniformly, and absolute space, which does not depend on physical events in it. In some sense, space and time for him is like a theater, and we are like actors doing some action, making some action in it. But this idea was turned around again by Albert Einstein, who noticed, first of all, in special relativity, that the property of space and time depends on how we observe it. And moreover, in the general relativity, he formulated the law of nature in such a way that gravity is observed as warping of space and time. So I would like to tell you a little bit about general relativity. Actually, I need to understand the audience. So how many of you are high school students? Raise your hand. How many of you are undergraduate students? And how many of you are graduate students? So general relativity is a very hard subject. And so I have taught it at graduate school at Caltech. It takes full 1 year to teach general relativity. Now, today I try to attempt to do that in 5 minutes. So I'm going to condense my 1 year lecture into 5 minutes. Okay, so it's very economical. But I cannot do it in full scope. So I will do it in the simplified setup where we postulate that we live in 2 spatial dimensions. So we live, of course, in 3 spatial dimensions and 1 time. But supposing that we were living in 2 dimensions. So in fact, there is a very interesting book about such a world. It's called, published in 19th century British Victorian era of British England, called Flatland. So where everybody is living in this 2-dimensional world. And people living there are sort of various geometric shape, like triangle, square. And according to this book, the more corner you have, the higher in the social rank. You know, Victorian era was very hierarchical. And so if you are triangle, you are like some lower rank laborer. And if you are square, you are like ordinary citizen, middle class citizen. And circle is the highest in the social hierarchy because you have, in some sense, infinite corners. And so this story is about this humble middle class Mr. Square in this flatland. So one day, Mr. Square was walking on the street of the flatland, and he noticed there is some kind of point in front of you. And then suddenly this point becomes bigger and bigger and becomes like a circle. And he thought, well, this must be somebody very noble. But then the circle becomes smaller and smaller and disappeared. So what happened? Well, so what happened was that the sphere, three-dimensional, he didn't know this, but this flatland was part of this three-dimensional space. There was an extra dimension to it. And there was a sphere living in the three-dimensional space, and it cut through this two-dimensional space, and so it looked like that. Okay? So then this sphere, Mr. Sphere, took Mr. Square to this spaceland and opened his eye to higher dimensions. So this is like the story of flatland. Okay? So when you go home today, as you're walking, if you start seeing some point, and it blows up to sphere and disappears, then perhaps we are living in four-dimensional space, and four-dimensional sphere just crossed in front of you. Anyway, so we are going to talk about this kind of flatland. So let's suppose that Albert Einstein were actually living in this two-dimensional space. Then what kind of theory would he have constructed based on the observation that if you are freely falling from the roof, you don't feel gravity? Okay, so this is the kind of theory that he would have constructed. So suppose you have this two-dimensional space, and suppose you have this kind of object which have mass. So therefore, there must be a gravitational attraction toward this object. How would you describe the gravitational force in this setup? Well, what happens is that if you have a massive object in here, then it's going to generate a cone around it in his theory. So what it means is that you're going to cut out this angle. And the amount of angle is proportional to the amount of the mass over here. And then you cut it out, and you make this cone. Okay? So what this cone has to do with gravity? Well, so suppose you have two straight objects. If there is no force acting on it, then there is the object should go straight. However, if it actually is on the cone, they're going to attract each other, just as if there is a gravitational force acting on this object. So you see that if the mass creates this conical structure, then the trajectory of this object behaves as if there is a gravitational force acting on it. So this is how Einstein would have explained general relativity. So Einstein's idea of general relativity is essentially like this, except that you have to do it in 3 dimensions, so it requires a little bit more mathematics. And that's why at Caltech, I need to use a full year of graduate course to explain it. But the basic concept is like that. And another important feature is gravity also warps time in addition to space. By that, I mean that if there is a gravitational force, then in the neighborhood, the clock runs slowly. And so extreme example is a black hole. Okay, so black hole is an extreme example where warping of space and time happens. And because of that, nothing can come out from the black hole. So here's another thought experiment we could do. So actually, there is my wife taking my photograph over there. And so she says that, she tells me that, will you go to the black hole and report to me what's going on near the black hole? Okay, so I say, I do whatever she says. So okay, so I am going to go to the black hole and I email you every day, report to you what's happening, okay? But then I do that, but then what's going to happen is very funny. So indeed, I start sending her email every day. But from her perspective, for a while she starts getting email from me every day. But then after a while, it's every week, every month, And then she started getting email only from once a year, once in 10 years. And then she looked at me, what's going on? And it looked like I'm actually procrastinating near the event horizon of black hole, hesitating to get in. So she's very angry and says, well, why is she procrastinating? But this is not how I experience it. I'm diligently sending her email every day and even crossing the event horizon. So you see that it depends on how who looked at this thing. But this shows that if you are near the horizon of the black hole where gravitational force is strong, then the time runs very differently. And this is actually very important. So I believe, I guess almost all of you has a smartphone like iPhone, the Galaxies, and it has GPS in it to tell you where you are and what time it is. And the way the GPS works is the following. So around the Earth, there are like many, 20, 30 satellites like that going around. And each of that carries very accurate atomic clocks and send time very precisely towards the Earth. So if you look at the sky and you see at least four satellites, if you can get signal at least from 4 of these satellites, then you can figure out what time it is and where you are. Why 4 satellites? Because if you know the time the time that was sent, the information about the time sent from the satellite, and you know what time it is precisely, then you can compare. And if you have 4 satellites, you have 4 equations. Now we have 3 space and 1 time. So by solving this equation, you can figure out where you are in 3 dimensions and what time it is. That's how GPS satellite works. However, as I mentioned, if you take into account the effect of special and general relativity, time flows differently. And so if you do not take into account this effect, in fact, the GPS would have an error about 10 kilometers per day. So it would be a very interesting thought experiment to think what things would have gone if Einstein were not born and special relativity and general relativity were not discovered. Well, I think GPS satellites would have probably existed because not much of how to build a GPS satellite uses special relativity and general relativity. So you can imagine a planet where intelligent life evolved and eventually launch a GPS satellite and expect it to work, and then discover that there is this huge error. So what's going on? So then they might have rediscovered special relativity and general relativity in this way. So that would be possible alternative history. Okay? So I told you the 4 mystery of the gravity. The gravity is a force, which is already a mystery. And gravity is weak. The gravity can disappear, and gravity is a warping of space-time. And I already said gravity is a warping of space-time. Now, the title of my book was, What is Gravity? So this could have been a perfect answer to the question, so I could have finished my book right here. But I had a few more pages in the book. And the reason is that, there is quantum mechanics. So that makes the story more interesting. So the second 3 mystery has to do with that. So in fact, gravity is very hard to be unified with quantum mechanics. So about 12 years ago, around this time of the year, it was announced that the Higgs particle, which is the last elementary particle in the standard model of particle physics, was discovered. This was a big deal. The Nobel Prize was given. And it was important because it completed what's called the standard model of particle physics, which describes sort of macroscopic world in a very precise fashion. And it contains these elementary particles, and this was the last particle. In the US, they sell a stuffed animal of elementary particle physics particle in this way. But there is a missing piece to it, which is that if you have a gravitational force, in the language of elementary particle physics, there must be a particle which sort of mediates a gravitational force. And that's called graviton, and that was missing in this table. And the reason is that it's actually not part of the standard model. Gravity is not a part of the standard model of particle physics. So somehow, the framework of quantum mechanics, which is essential for standard model of particle physics, does not work well with the gravity. And the reason is the following. So gravity, as I said, is a warping of space and time. But as you might have heard the word uncertainty principle, things are uncertain in quantum mechanics. So in classical world, if you throw some object, you can solve Newton's equation and tell the trajectory exactly. But in quantum world, all possibility exists simultaneously. So things are very uncertain. So what that means that any attempt to unify gravity and quantum mechanics would make space and time uncertain. So how do you formulate the theory on the space and time which themselves are uncertain? And so reconciling the quantum and gravity has been the holy grail of modern physics, and we are still sort of struggling to complete this program. And the only consistent way we know how to do this is a superstring theory. So this is why the study of superstring theory is a very big part of our quest towards the most fundamental laws of nature. The superstring theory postulates the fundamental building blocks are not point particle, but some extended object, strings. And this theory has helped solve some of the deepest mystery of quantum gravity, such as the origin of Hawking radiation from black hole. So that's why we are very excited. String theory not only unifies the general relativity and quantum mechanics, but there have been several important outstanding questions about gravity and quantum mechanics, which have been solved by superstring theory. So let me change a gear a little bit and go to pose the sixth wonder of gravity in a slightly different angle, which is that the question of why the sky is dark at night. Okay? So I said at the beginning that the gravity is a mysterious force, and this seems to be contrary to our intuition, because for us, gravity seems to be very familiar, but I hope I explained to you that there are some mysterious features of gravity. Similarly, what you may think is a very obvious thing may have actually profound implication. So for example, I would like to ask you, why is the sky dark at night? Well, so obvious answer is that there is no sun at night. But that's, of course, is part of the answer, but that's not the whole answer. So let me explain why. So around the Earth, in addition to the sun, there are other stars that are shining. So let's try to count how many stars are there and how much light we get from these stars. So suppose we go from the sun ourselves to about 100 million light years away. Okay? And then you count the number of stars around there. Okay? So then each of them shines with certain light. Now, let's go twice as far from that point. So 200 million light years or something like that. And then you see that if the distance becomes twice, the area becomes 4 times, 2 times 2. So that means that if you go twice distance from the Earth, there will be 4 times more stars there. But each of them shines less because there is the inverse square law. So if you go farther away, the light becomes weaker. So if the distance to the star becomes twice as long as far, then the light from each star is like a quarter. Now, this is interesting mathematics, because that means that if you go twice as far from the Earth, you have 4 times more stars, but each of them shines quarter of the original stars. Okay? So what it means is that the amount of light you get from all the stars to 1 million light years, or Earth to the 2 million light years, is actually the same. If it goes to 3 million light years, it's the same. So that means that however far you go from the Earth, if you count the light from all the stars from there, you get exactly the same amount from any distance. So if you add them up, then the sky should shine infinite brightness. That's not what we observe, right? So this was actually called Olbers paradox, where this was actually, as many other things, evidently this was not first observed by Olbers. Even like Kepler realized that there is something funny about this kind of infinite universe. So this poses a question of why is the sky dark at night? Even though this type of reasoning seems to suggest that sky should be infinitely bright. Okay, so what's going on? So to my knowledge, the person who first answered this question properly was Edgar Allan Poe. That you might have heard of him as, for example, the first person who wrote a detective novel. But he was multi-talented, and he has some good idea about how to go about solving this problem. So here is some kind of essay that he wrote called Eureka. And in this passage, he describes basically this Olbers paradox. But then he said that you can actually explain it if you suppose that distance of the invisible background is so immense that no ray from it has ever been reached to us at all. And this was like correct way toward answer the question. So in fact, something like that was confirmed in the 20th century. In 1929, Edwin Hubble announced that the distance galaxies are receding and the recession velocity increases with distance, implying that the universe is expanding. So here is a photograph of Albert Einstein visiting Hubble in Mount Wilson and checking out his telescope. When I showed this, when I talked about this photograph with a professional astronomer, she said that this photograph must be staged. Well, first of all, you won't be able to see just this telescope and say, oh, the universe is expanding. That is not possible. But more importantly, this type of astronomical instrument is very precise and delicate, so you will not smoke pipes next to such instrument. So anyway, so this is a photograph of Einstein Hubble, and a few years before he published that the universe, well, he didn't say that the universe was expanding in his paper, but it was implied from this observation that the universe is expanding. So if the universe is expanding, then if you go backward in time, there must be a time when the universe was hot and dense. And so that's called the Big Bang. So in fact, Einstein's general the gravitational equation predict that if the universe is expanding by solving this Einstein's equation, you can actually inevitably predict that the Big Bang or something like that, some kind of singularity must have existed. In fact, this is a mathematical theorem proven by Roger Penrose and Stephen Hawking. And now we can actually observe some of the earliest stars that appeared after the Big Bang from 13 billion years. But that does not mean, that means that universe, we cannot see infinite distance from the Earth. Because if we go something of the order of 13.8 billion light years away from it, in fact, the universe is expanding, so the distance is slightly different. But if you go certain distance away, then you go back to the beginning of the universe, so there was no star over there. So the Olbers paradox can be solved in that way. So, so this, of course, raises a lot of interesting questions about what happened before the Big Bang and how can we observe the universe before the Big Bang. But as you can see, that the question such as why the sky is dark at night is a very profound question. This sounds like an obvious question, but if you think about it properly, it raises a question of whether the universe is infinite or whether you can see infinite distance from the Earth, or whether such assumption is correct or not. And in fact, the Big Bang cosmology suggests that the reason that the universe is dark at night is because of the existence of the Big Bang and the expansion of the universe afterward. Okay? So that's the sixth wonder of the gravity. So the last mysterious property of the gravity is that gravity seems to be tuned just so that we can exist. And this is very mysterious. So the universe was born in 13.8 billion years ago. And this is actually really amazing that we know about the age of the universe with these three significant figures. When I was a graduate student, actually there was a dispute among astronomers, and their estimate of the age of the universe differed even by factor of 2. And in some estimate, the age of the universe was actually shorter than the age of some of the stars, and that was very contradictory. But anyway, so now, thanks to the precision measurement of various cosmological parameters, we now know the age of the universe in these three significant figures. And this was important. The fact that the universe existed such a long time has been very important because we know that the Earth was formed about 4.5 billion years ago, and the first living object probably emerged a billion years afterwards. But it took like 3.5 billion years for a very primitive living object to evolve and become Homo sapiens, intelligent enough to ask, like us, what is gravity? So we need a very, very long time. Okay, but why the universe is so, the age of the universe is so long, and is closely related to the fact that gravity is weak. And so, for example, the gravity were weaker, then the star and the planet would not have formed. And so there is no possibility of creatures to be evolving on this object. But if gravity were stronger, most stars would not have collapsed into black holes. So again, it would have been impossible for us to exist in such circumstances. So it seems like the gravity is behaving in such a way that the universe exists a long time and we have this hospitable environment, so to be able to evolve like that. So some people think that there's this idea called the anthropic principle to explain this, but some of us differ from this opinion, and some of us are still hoping that we can explain it from the first principle. So there have been lots of interesting debate about this kind of question too. So anyway, during this presentation, I described these 7 wonders of the gravity. So gravity is a force, and gravity is weak, and gravity can disappear, and gravity is a warping of space and time. But it's hard to be unified with quantum mechanics. So that was the first part of the discussion. But there are other mysterious things that gravity can explain, such as why the sky is dark at night. And it's also raised the question of why the gravity is just so that we can exist in this way, and it poses lots of interesting questions. So this was sort of introduction to this book, What is Gravity? And this was sort of whet appetite of the reader. And then the book goes on to discuss special and general relativity in more detail and quantum mechanics, and introduce a notion of superstring theory and the Calabi-Yau manifold, black hole information paradox, and the holographic principle, and all in one book. So if you read this book, you get some idea of what these concepts are like. And as I said, this book actually inspired us to make 3-dimensional science movie called The Man from 9 Dimensions, and it appeared in 2016 and actually got the Best Educational Production Award from International Planetary Society, which is the highest award. And it has been actually shown in many countries. In Germany, it has been actually continuously running in Hamburg for many years. Last year, I went to Munich to show this movie and translate it into 6 languages. This was actually the photograph of the show that we did in Mumbai. So we had a Bollywood debut of this movie. This is when we showed it in Hamburg. And one of the important players in this movie is a Calabi-Yau manifold. So when you go to the museum in Tokyo, where this movie has been shown continuously for the last 8 years since this has been released, you can buy T-shirts of Calabi-Yau manifold. And Professor Yao kindly is wearing this T-shirt. You Tokyo and look at this movie at the planetarium. So we'll show you this movie tomorrow. I wrote a few other books. So this is actually in this book called Superstring Theory. This explains superstring theory in more detail, and it actually received a Science Book Prize. And when I come to Tsinghua last time for Strings Conference in 2016, actually there are quite a few students who had this book, and so I wrote some autograph on some of the book. I was just talking to the publisher of the book, and he was telling me that this book actually sold 60,000 copies in China so far. I also had this book about standard model of particle physics, explaining things like Higgs mechanism. And then, so this book is actually one of my favorites, where I explain various concepts of mathematics like Bayesian statistics, incompleteness theorem, and even Galois theory in a way that is sort of appropriate for high school students. And in fact, this has been used in various liberal arts colleges in Japan. And this is a book that is sort of slightly different flavor. This is actually my autobiographical book. And this was sort of my pandemic project that I wrote this book in the first year of pandemic. And in the introduction, a preface of the book, I actually explained why I wrote this book. I felt that I was still too young to write autobiography, so I had to explain why I wrote this book. And so here is the introduction, preface of the book. And what happened was that about 5 years ago, during the routine health exam, it was discovered that I had a prostate cancer. And prostate cancer, as you know, is very curable when it is localized. But in the subsequent exam, there was some indication that it might have metastasized. So if it is metastasized, it's not curable. So it was actually even more shocking than when I discovered that I had prostate cancer. So I immediately canceled all my trip and scheduled a surgery as soon as possible. But there was one trip that I cannot cancel, and that was a trip to Tokyo, because I organized some kind of event at the biggest lecture hall at the University of Tokyo, and I was the first speaker. So I went to this conference just before I got the surgery. And while I was waiting for the airplane, I got an email from one of my publishers inviting me to write an autobiography. So in fact, I got many offers like that before, but I thought I was too young to do that, so I declined. But since I got this email right after this cancer diagnostic, and then I was about to take the surgery, so well, I thought maybe somebody is telling me that I should do it. So I accepted the invitation to write the book. Fortunately, the surgery was really successful. The doctor discovered that cancer is completely localized, and he was able to take everything out. And in fact, that was already like almost 5 years ago. And every time I do the test, the cancer marker is undetectable. So my doctor says that he doesn't believe that there is any cancer left in my body. So I'm really grateful, and I felt reborn after this news. So I wrote this book feeling very grateful, and so I recounted my life as a sort of scientist. And then in the second half of the book, I also discussed the importance of basic science in the society. So this book turned out to have a big impact in Japan, and it was read by politicians and policymakers. So for example, recently, Japanese government set up $70 billion endowment for universities in Japan, which produces several $billion every year. And so I was asked to put a panel to actually select a university to get the benefit from this endowment income. And so this book has helped us in many ways in basic science too. And so I often get asked why I write so many popular science books. And often I quote this word of Thomas Aquinas. He was, of course, famous Christian. I'm not a Christian, but this word resonates with me. So he said that better to illuminate than merely to shine, to deliver to others contemplated truth than merely to contemplate. So this is sort of one of the reasons why I try to sort of, so I still feel that my main job is a professional scientist, and my job is to discover truths in my case, mathematical physics and theoretical physics. But I think it's also interesting and important to sort of convey the excitement of this science to a broader general public. So that's sort of one of the reasons why I do that. Thank you very much for everyone.
Yeah, thank you very much for this wonderful talk, Professor Oguri, and we all hope that you have a very long life ahead.
Thank you very much.
So that you can write many more books.
Now I'm certain of this. Thank you very much. So one thing I want to do is that the kind of work I do is useless science, but this experience made me appreciative of useful science too, like modern medicine. So thank you very much.
That's great. Wonderful. Yeah, questions from the audience. Yeah.
Hello, Professor. I see that you are interested in like string theory.
Yes.
And I have read Hawking's book. Hawking's book about the Hawking's. I forgot the name, but it is a Hawking book for the ordinary people to understand. And it says that in string theory they have additional dimensions. And I'm curious about the nature of the additional dimensions.
Okay.
I wonder if it is only technical or it have some physical like phenomena in it. Yes.
Thank you for asking an interesting question. So in fact, it's interesting that string theory has extra dimensions, but it's more interesting that string theory actually fixes the dimension in the following sense. So if you look at any other laws of nature, such as Newton's law, not nature, physical world, like Newton's law or Maxwell's electromagnetism, you see that you can formulate any of these laws in any dimensions. Newton's law, you can write, well, we use Newton's law to describe motion of the object in 3 dimensions, but you can write down Newton's equation in 5 dimensions or 11 dimensions or a million dimensions. Similarly, you can write down Maxwell's equation in any dimension. So but interestingly, string theory it's not possible to formulate string theory in any dimension except for certain dimension. In a what's called weakly coupled string theory, it's only possible in 9 space and one-time dimensions. And this is very interesting because I don't know of any other laws of nature which makes us hope that we can explain why we live in 3 dimensions. But in string theory, at least we start from 9 dimensions. So there is something to start. So if you can explain why 6 extra dimensions are not visible in our ordinary life, then there is a hope that we can, in principle, explain 3 dimensions. So in fact, string theory is defined in 9 spatial dimensions, is actually a sort of blessing in disguise, in some sense. And this extra 6 dimension plays a very important role. If you solve the equation of motion of string theory, then it is determined that it should be described by what is called Calabi-Yau variety or Calabi-Yau manifold. And it has a very rich structure. And one of the very interesting things is that what we experience in 3-dimensional space, our 3-dimensional space, is sort of described in the geometric data in Calabi-Yau manifold. So for example, if you look at the standard model of particle physics, it has lots of structure. It has 3 generations of quarks and leptons, and you have intricate gauge interaction, and Higgs mechanism to give mass to the elementary particle and break symmetry spontaneously, as Professor Waffer said. All these features are encoded in the geometry of Calabi-Yau manifold. In fact, I was a first-year graduate student in 1984, where all these developments happened, including the paper by Candelas, Horowitz, and Strominger and Witten, where the word Calabi-Yau manifold first appeared in the physics literature. And I was very, very impressed by the fact that this complicated and intricate structure of the standard model of particle physics are all beautifully encoded in the geometry of Calabi-Yau manifold. So in fact, I think that having this extra dimension is again blessing in disguise. Without this kind of extra dimension, I cannot imagine how you can sort of deduce this type of structure of standard model of particle physics from fundamental principle. But having to start from 9 dimensions and having this Calabi-Yau manifold, and it's very interesting that 9 is equal to 6 plus 3. That Calabi-Yau manifold is just there so that you can go from 9 dimensions to 3 dimensions, so that you can actually hope to explain the model of elementary particles that describe our universe in terms of this kind of geometric structure of Calabi-Yau manifold, and then therefore from the fundamental principle. So I think that this extra dimension plays many important role in our understanding of fundamental laws of nature in this way.
Thank you. Other questions?
Hello, Professor. Has there been any attempt made by artificial intelligence in solving cosmic series?
Artificial intelligence too? Could you read the last part?
Cosmic series.
Solving cosmic series. Yeah. Well, so there has been some attempt to use artificial intelligence, but not in a sort of major way so far. One attempt has been that there have been actually variety of ways from going from 9 dimensions to 3 dimensions, because there are various different types of Calabi-Yau manifold. And so there are some physicists who are trying to train a machine learning program so that you can actually discover the most favorable way to go from 9 dimensions to 3 dimensions and fit with standard model of particle physics. So far, it has not been completely successful, but I think it's an interesting direction. Yes, so there has been some attempt. Yes.
Okay. See more questions? Yes. There are many, so let's go here.
And good afternoon, Professor. And there's an extension question from the first question. And according to the string theory, we know that there are 6 dimensions more. And so we humans are familiar to the gravity affecting us on the 3-dimensional space. And if in the far future, we're going to have a possibility that we are able to release the other dimensions, even 1. And at that time, does that mean there will be a new force, a new gravity affecting us on a new direction? And will that cause a devastating effect on the world?
Yeah, so, well, thank you for your question. I think that, well, it depends on what the definition of the force. So so far we have 4 kinds of forces. But if you think of force as a sort of effect that is that happens by exchange of particle, then if you go to higher and higher energies, there will be more sort of elementary particle emerging, and the exchange of that can, in principle, produce more type of forces. So, for example, if you hypothetically build a very high energy accelerator, so energy so high that you can, for example, vibrate Calabi-Yau manifold, or maybe excite certain mode of Calabi-Yau manifold, that might behave as a sort of new type of elementary particle that mediate a new type of forces.
Do we have other questions? Yes.
Thank you, Professor. We know that if we want to compute the radius of a black hole using Newtonian laws, if we suppose the radius of a black hole is just exactly the place where a photon cannot escape,
yes,
we get the
that's an interesting coincidence. Yes, yes.
Get the formula 2mg over c.
Yes.
But if we use the Einsteinian equation and get the Schwarzschild metric, we get exactly the right formula. But we also know that Newtonian law is only a poor approximation, neglecting the higher orders. So is it a matter of coincidence or?
Well, it's a coincidence in a sense that there are 2 effects. that are canceling each other when you try to do this calculation in Newtonian approximation. As you said, Newtonian approximation should not be applicable in calculating the event horizon. But somehow, as you pointed out, it gives you exactly the right, even the right coefficient in 4 dimensions. And so it's interesting. But it's actually, if you look at it, it's basically, there are 2 effects that are canceling each other.
Oh, thank you.
I saw that there were some questions there. Yes?
I have a question. What's the relation between 7 fundamental physical quantities?
So sorry, what's the relation between 7?
7 fundamental physical quantities.
What are 7 quantities you are referring to?
Yes.
Sorry?
What is the relation between the 7 fundamental physical quantities? I think you refer to the 7 quantities of gravity, which were, or 7 properties of gravity, which were mentioned, and you ask whether there is a relation between them?
Well, so are you referring to, so let me try to understand the question. So are you referring to these 7 questions, or? No.
So
you must be talking about something.
Several?
So I'm not sure what you were referring to as the 7 fundamental concepts. For example, standard model of particle physics has 16 parameters. And then the standard model of cosmology has 6 parameters. And so I'm not sure what 7s. Where does the 7 come from?
Oh, that's okay. But so you count 7 exactly.
What are those 7s?
Maybe since you know, you can tell the audience.
Maybe in the SI, the international about the units like meter, time. Meter means length, and time, the second, and so on. The 7, the candela, molecules.
Oh, you are talking about units to measure quantities, like distance, time, weight, energy. Are you referring to those things?
Maybe that's the meaning.
Yeah, it seems it's not clear, but
yeah, actually, I highly recommend you to read autobiographical note of Albert Einstein. In his book, he has actually beautiful description of what's called the natural unit. So in nature, there are various fundamental constants, such as Planck constant, and the gravitational constant, and a speed of light. And if you use these fundamental constants, actually everything in nature can be measured by quantity without any of these units. And these are called natural units. And Einstein's autobiographical note have a beautiful explanation on this.
Thank you. One last question. Okay.
Good afternoon, Professor. So what's the biggest difference between math and physics, and how did they help humans' life?
Thank you. So the big difference between physics and math is that physicists try to understand this world in the narrow sense, the world we live in. And the mathematicians are interested in a sort of patterns and structure in a more broad sense. And in some cases, the structure that they study may not immediately describe our nature, but surprisingly, very often, the tools they develop found application to understand nature. But most of the time, the aim of mathematicians is not explain our universe as it is in a narrow sense, but in a sort of more Platonic sense. There are many mathematicians who believe that, in fact, there is a mathematical world, this idealized world, and they are exploring this world. But physicists are trying to understand this world. So that's sort of a big difference between them.
Yeah, thank you. So let's thank Professor Oguri again. please remain on the stage, and I would like to ask the other distinguished Yao and Professor Wafa and Professor Valiant to come to the stage for the book gift.